Okay, that seems like a good list to me. Cool. All right, didn't ask me about these two chapters, which is fine. Just to quickly say, this is just your stoichiometry titration calculations here, and identifying an oxidizing or reducing agent. This one is basically going to be, if it's not a conceptual question, it'll be like rank these ions or atoms in order from decreasing to increasing size. Okay, so that's it. This one should be a fairly easy question, I hope. All right, let's start. Let's just do chapter 6 first. I'm going to do the real gases and the compressibility stuff first. I think I can bust that out pretty quickly. This is in your reader on page 50, essentially. I could ask you a couple of things about this. One type of thing I could ask you is a conceptual question, which means like, for example, what does this NB term mean? That NB is a volume correction term. One reason that you might have a volume correction, this is all on page 50. One reason you might have a volume correction is the assumption that molecules are tiny does not hold. So molecules actually take up the volume. This is right there, that term is a pressure correction. An example of a pressure correction would be, say, the assumption that gases don't interact would be not true. So if the gases actually are attracted to each other, that would change the pressure. And that term accounts for that pressure change. So these two terms are there because you can see it pretty much looks like the ideal gas law. EV equals nRT. Those two extra terms are there to correct for non-ideal behavior. The other type of question that won't go into detail, but I will refer you to the practice exams. And if somebody wants to ask me during the specific question time, if you look, I think either on the most recent practice exam or the one, it was either that one or the one before it, I did have a calculation with this. Yeah, it was winter 2014, 1 year ago. I had you do the same calculation in part A and B, but in B you had to use a real gas equation state. You knew you had to do that. One, I said that. And two, I gave you A and B. So from there, it's plug and chug. So if somebody wants to ask me that after, I'll go more detailed using this formula. But otherwise, know the concept. And then the compressibility factor says that if you take the ideal gas law and divide through by nRT on both sides, you get 1 on the right if this is ideal. So it's an easy way to check if I have an ideal gas. You just take, if we give you P, V, N, and T, calculate this, see if you get 1 or a number within 10% of 1. If so, we're considering this an ideal gas. If it's much off of that, we consider it a real gas. And that's all this tells you. Is it a real gas or ideal gas? And really it's a continuum. It's not like this is real, this is ideal, but something gets more and more real or less and less ideal. All right, that's all I have to say about that. So this would hopefully be a quick calculation for you. Just checking to see if you get the number 1. All right, let's do some units next. Units. And then we can use that when we do some other practice problems. You need to know, I will not tell you that a Newton is a kilogram meter per second squared. You need to know that a Pascal is a Newton per meter squared, and a Joule is a Newton meter. So those 3 you want to know, I will not tell you that. But you should be able to use that. So somebody asked me about the rubin square velocity. I'll give you this equation. Okay? But you would want to be able to mess with the units. So since somebody asked me, let's just do an example. Let's say I have a gas xenon, and let's say I'm at a temperature of 300 Kelvin. So if I wanted the rubin square velocity, I would go, okay, 3 times R. This is, remember, it's the R with the joules in it. It's not the one we use typically for the ideal gas law. And, or another way to say it, this is the one with the SI units. So it's this R, we'll give you both R's, you just need to pick 1 over m. Okay, turn to your neighbor for a second. What am I going to put down here? I'll give you like 10 seconds. Is this right? That's not right because, yeah, this is an SI units question. I need to change this to kilograms. Everything else is in SI units, and that's in grams from the periodic table, so you need to make sure to change that. That's the most common mistake. I scared somebody. It's okay, it's not that crazy. This is the most common mistake on this type of calculation. I just made this up, so I don't have an answer for you, but typically the answer is in the hundreds or low thousands. That would be a normal answer, in the hundreds or low thousands, so just check your answer, make sure you're on track. Okay, let's look at the units though. You have a joule per mole Kelvin times a Kelvin divided by a kilogram per gram times a gram per mole. So you get your other pen color out, grams cancel, the kelvins cancel, the moles cancel, and you've got joules per kilogram. Let's evaluate that a little bit. Now you want to use this information I told you earlier, and you say, okay, I know what a joule is, that's a Newton meter, and I'm divided by a kilogram. That doesn't help me, but I know what a Newton is. A Newton is a kilogram meter per second squared. That's times a meter divided by a kilogram. Notice what happens. The kilograms drop out. The meters combine to make a meter squared. And remember, this was all under the square root sign. Up here, it's all under the square root. So when I take the square root of that, I get a meters per second, which is a velocity unit. That's what I would expect. So typically, not only when you're working out problems, you need to get the right units, but I might randomly, as you see in pretty much every test, so I hope you looked at the tests, I almost always, no, maybe I should say always, give you a unit calculation question in the multiple choice because I just want to make sure you got it down. So let's say I gave you a joule second divided by a kilogram divided by a meter per second. And I said, simplify this. You're like, okay, that's cool, let's do that. A joule, the seconds flip up, so it's seconds squared, kilograms, meters. And now let's simplify the joule. The joule is a Newton meter. So I still got the second squared, I got the kilogram, I still got that meter there. The meters cancel. Now I still have to simplify the Newton. A Newton is a kilogram meter per second squared. That's the Newton. I still got the second squared, and I still got that kilogram. Notice the second squareds drop out, the kilograms drop out, and all I'm left with is a meter. Oh, sorry, a meter. Okay? So this kind of simplification, if I gave you that in multiple choice, I'd expect you to be able to do within about a minute or so, maybe 2 minutes. Okay? You'll see them on every exam pretty much. Once I thought of the question, it's on every exam. Okay, so that was units and Rubin square velocity. Let's do Graham's law really quick since we're on that. Graham's law has a couple different possible iterations. Remember, it's the property of gas 1 divided by the property of gas 2 divided by the inverse of the molar masses. This works for 4 different properties. It works for the Rubin square velocity, it works for a distance, it works for an amount, and it works for time. Okay? So those 4 could be sample properties. Which one is the oddball of those 4? Time. You can even tell the way I wrote it. It's the one on the right, and it doesn't have a friend. Time is odd because, this you have to remember by yourself, I won't remind you, on an exam I won't remind you, is that if you have the equation for time, it's time 1 over time 2, and it's the molar masses are not inverse. Okay, that comes out in the derivation. Everything else, the molar masses are inverse. This type of question, whatever the property is, can come in a couple different ways. Either we'll ask you for this ratio. First, you're going to see two gases. That's a big hint, it's one of these. And then we're either going to ask you for that ratio on the left-hand side, which is just the ratio of the molar masses, or we'll give you, say, one of the variables on the left-hand side and have you solve for the last one. So a typical kind of question would be, of those two, like let's say we have two gases, it doesn't matter what they are. Let's say we have fluorine gas and argon gas, okay? And I wanted to know the ratio of distance traveled of fluorine gas to argon gas. So D for distance. So they say, okay, he wants to know the ratio, he wants to know this. Well, that's just the inverse of the molar masses, so write that. There's the inverse of the molar masses. And then I write these molar masses in here. So argon is 39.95 grams per mole, and the fluorine, 2 times 19, so that'd be 38 grams per mole. Do I need to do anything with these units? Okay, so I'll say it this way. Do they need to be in kilograms like the root square velocity?
No.
They do not. If you put them in kilograms, that's fine. You're just wasting your time and valuable exam moments. Because they're both in the same units and those units divide out. So if you change them to whatever, they still divide out. If you change them to pounds, they'll still divide out. By the way, which one will go faster, argon or fluorine gas? Okay. Okay. Which one is lighter? The fluorine's lighter, so it will go faster. The lighter ones go faster. That's the general concept we got out of the kinetic theory of gases. Okay, you'll get a number, it'll be a little bit bigger than 1. Okay, you can find that up here. Okay, next, we're rolling. I'm loving this chapter right now. We just did a UR, which you are sometimes. We did that. We didn't do the kinetic energy. Let's do that. Kinetic energy. Remember, there's two formulas and two formulas only. 3/2 RT, and I will give you the second formula to look like this, but in reality, you want to write the second formula as 1/2 molar mass, root mean square velocity squared. Okay, so it's really this formula, and you're going to rewrite the middle formula as that. Okay? Now, typically, which one did I recommend you use? The one on the right or left? The left, because it's easier. There's just one variable, the temperature. So if I went back to that previous problem I did this previous problem, oh wow, way back there, of xenon. Remember the xenon question? Okay, so let's try this xenon question for the kinetic energy. Remember, really, EK squiggly means kinetic energy per mole. Okay, here we go. So I prefer this 3/2 RT. What kind of units am I looking to use here? SI units is what I'm looking for. So if you said the 8.3145 R, you're correct, because this has joules per mole Kelvin. Really, in chapter 6, a lot of these plug and chug questions are you prefer the SI units. It just makes the problem easier. In the case of the xenon question, I said it was 300 Kelvin, and this would give you the kinetic energy. I'll let you calculate that. Notice the units will be in joules per mole because the kelvins will cancel out. And joules per mole is your EK squiggly unit. What if I change gases to fluorine? We used this last time. What's going to happen in my calculation? Turn to a neighbor. What will happen if I change the gas from xenon to fluorine? My calculation, what would happen? What happens? Yeah, nothing. Okay? It's the same. Why is that? Because the temperature didn't change. Since I did not change the temperature, nothing changes. Okay? So that's sometimes a tricky one. You need to know for any gas at the same temperature, you have the same what we call average kinetic energy. Well, you'll really see those terms. So technically, if you see a question where I say, will the kinetic energy be the same for these two groups of gases for any given molecule? You should say no. But for any given molecule at the same temperature, on average, the kinetic energy will be the same. So the key word is really average, and that's what we always calculate. We're always calculating the average. Yes?
So does the gas being diatomic not affect the average kinetic energy because it's actually the...
Yeah, does it affect it because it's diatomic? No, not at all. Yeah. One would go faster than the other. Which one would go faster, everybody? Xenon or fluorine? Fluorine because lighter, 38 grams per mole versus 131 grams per mole. That's what would change, but not the kinetic energy. Yes?
How can you tell the difference between the ratio of fusion rates between boron to gas and xenon?
The ratio of diffusion rates?
Yeah.
Yeah, if you wanted to bust out a Graham's law, the ratio of diffusion rate, so that's the root mean square velocity of, repeat the question again, what to what?
Well, on this problem, it was,
It's okay, you just choose. Do you want to say fluorine first verbally, or do you want to say xenon?
fluorine to gas.
Okay, so that means the fluorine is the numerator. That's all I needed to know. So read the question carefully. Whichever one is stated first has to be the numerator, and the second one here is xenon. So it would just be this. Is that okay? And these can be in grams per mole, both of them, because it's a ratio. Okay. Cool, let's move on. Next is Dalton's law. Maybe I should specify with you all. Do you want me to focus on the Dalton's over water?
Yeah.
Okay. That's fine. If you need Dalton's law examples, remember that you can always look on the YouTube channel. I've got plenty of those as well. All right, for Dalton's over water, what does that mean? We don't always specify what the reaction is, or the experimental setup I'll draw for you, but the key words you're looking for are something to the effect of collected over water. If you see those words in any sort of arrangement, it's this kind of question. So looking for collected over water, and sometimes there's only one gas usually, but there can be more than one gas too. Okay, so the experimental setup would look like this. There's a reaction occurring, and a gas is produced. And there's this tube that the gas will come out of. And that tube will go into a container with water. So let's draw a little container here. There's water in this container. And then this container will have an upside down tube, like a graduated cylinder or something like that, that is filled to the top with the water. What happens is, as the gas bubbles out through the water and into the tube, the top of the tube starts to fill with gas, because the gas goes to the top and it pushes the water out. We'll do an experiment like this at the end of the quarter. So it goes to the bubbles to the top, and we have some I'll just say this is the gas forming here. Okay? Now, that gas, it has at least two parts. It's the partial pressure of the gas produced from the reaction, whether it's one gas, two gases, five gases, whatever, and what other magical gas? water. The water vapor, the water produces a vapor we call water vapor, and it has a certain vapor pressure of water that is also mixed in with the gas. So anytime you will have water and whatever the reaction gas is. So this would be the reaction gas. Okay? So what's going to happen is this number is either given or atmospheric pressure. This one usually you're going to find, and this one is from a table. On the exam, I would not give you that number. You would have to know to go to the back page of exams, and I'm showing you here the practice exams, the exam 2 givens. Okay, it's all on my practice exam reader. This table right there, this is where you get the vapor pressure. Okay? On my test, you usually see it one of two ways, if it's on the test. One is, sometimes I've just asked a multiple choice question that is super easy, but you might not feel that. Where I say, the temperature of this, of some water vapor, say is 50 degrees, and the container is 3 liters, and blah, 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 random. And then I say, what's the partial pressure of water? And you need to look at the 50-degree C and go straight to the right, and you say it's 92.51. So sometimes I literally see if people can read this table. If I want to make the problem more difficult, then it's a collected over water sort of problem. So this is the table I'm referring to. It's going to be on the exam. You may use it if there's one of these questions, you would definitely use it. So you need to remember to look at the back. That's from the table. And then there's a second equation you often use when you're doing this problem. It's this. The ideal gas law, where this value that you find goes into the ideal gas law, and typically we ask you for the moles of the gas, or sometimes, oh, that's a little hard to see, huh? Let me say it again. This P gas goes into the ideal gas law. We ask you for the moles of the gas given all the other variables. Okay? And then the mass of the gas, sometimes we'll ask you just to convert from the moles. So for a typical sort of question, where you'd have to use these equations, do you want me to go through a sample?
Yes.
Yeah. Okay. So let's say we had some reaction, and chlorine gas is produced. Okay? And I'll tell you the atmospheric pressure in that room, pressure was 750 millimeters of mercury. The temperature was 27 degrees C. And I want to know the moles of Cl2 gas. That would be kind of your pretty much straightforward sort of question. How would you do this sort of question? You would say, okay, well, I've got this equation, P total equals P of the gas, that's Cl2, plus P of the water, because this is collected over water, example. And you would say P total, I gave you that number, that was 750. PCl2, I don't know that. PH2O at 27 degrees C, hopefully I picked a number, oh, hold on. I need to pick a number that's on the table. 30. Okay. 30, magically I said 30. You go over here and you look at this table. I'll zoom in so it's easier to see. 30, so the partial pressure, or what we call the vapor pressure of water, is 31.82. Remember that number for a moment. 31.82. That is this number right here. So this is straight from the table, remember that table. And I want to solve for PCl2, or the partial pressure of Cl2. 750 minus about 32, that's 18. Is that right? Oh, you want to zoom out? Y'all want to zoom out? I understand, right? Okay. You want to see what I'm writing. What, 718, did I do my math right?
Yes.
Yeah, cool. Okay, so that's that. If I want to find moles of Cl2, I'm using the ideal gas law. PV equals RT, but it's PCl2, which I just found, V over RT. 718 millimeters of mercury times V, oh, I didn't do volume. 1 liter. Reads 1 liter over R times T was 30, I add 273. Okay, I made one thing, or there's one problem here. What's the problem? You got it, fantastic. That's a really common mistake. Millimeters of mercury do not match with the units that I did not write here on purpose, because I know you will not write them either. Okay, which are atmospheres. So I need to make that conversion. Let's do that. I'll just do it right here. I'll give you that conversion on the exam somewhere on the back. That 760 millimeters of mercury is 1 atmosphere. Whatever that is your answer. Okay? Any questions on this problem before we move on? Okay. All right, let's see what else we got here. I think we finished chapter 6. That's awesome. Crushed it. Okay, let's go on.